Hello all and welcome to Physics with Pranav. If you're new here, I'm Pranav. I was a former CAIE student in science and math. I tutor students from around the world in GCSE physics and ASNA level physics. And I'm also a former IGCSE world topper in science from back in 2013. So if you are a GCSE student preparing for your physics exam while you're also preparing for a load of other exams, um, the two key questions in your mind is what are the key topics that I should look at so that I can get the maximum bang for my buck, i.e., what do I need to focus on so I can do as well as I can? And how do I apply these key concepts in past paper questions so that I can get the grades that I want? So I have a very simple methodology which I'll be introducing you to in my videos that has helped me and that has helped my students achieve excellent grades in their exams. And I hope that this method helps you as well to achieve the grades that you want in your physics exams. So it's a very simple three-step approach. The first step involves looking at recent past papers to try and understand what are the most commonly tested topics. So this is a method that's grounded in data. So I'll say this as well, right? There's always going to be a question or two that can surprise you that's probably not been tested in the last few years. So it's always generally a good idea to look at the whole curriculum. But if you have to prioritize and try and get the maximum benefit and outcome out of your preparation, then it's important to know what key topics to focus on. So that is why the first thing we do is to prioritize by looking at recent past papers. The next thing after that is once you identify the key topics is to solidify the foundations, right? What exactly do these topics mean? What are the key concepts behind them and how do I apply them, right? So that's the second thing that we'll be looking at. And the third step to my approach is to actually put it into practice, right? So this is by looking at past paper questions and actually trying to apply these concepts there. How are you going to get the grades that you want to be able to get? So typically the way I've done my videos up is I'll split them into two. The first video tends to focus on the topics themselves, and the second video tends to focus on applying these topics to past paper questions. So in today's video, we're going to look at chapter 3 of the CAIE IGCSE curriculum, which is forces in motion. I do want to say that any GCSE student, irrespective of whether you are doing your CAIE or otherwise, you would still have an equivalent chapter. It might not quite be your chapter 3 if you're doing it Excel or AQA. It might be another chapter perhaps, but the concepts are still interchangeable. So I strongly believe that you can still take a lot of value from this video, as well as the video where I show how the concepts covered in this video will be applied to past paper questions. So without further ado, let's take a look at the concepts that are most tested in the forces and motion topic in IGCSE physics. So my approach, again, starting off with step one, is to look at the most recent past papers. So I've taken 2020 to 2022. I've looked at paper 2 and paper 4. So paper 2 is your multiple choice paper. Paper 4 is your theory paper. I've looked at all the variants within these papers. So that's 2-1, 2-2, 2-3, and 4-1, 4-2, 4-3. And I've also looked at the summer version, which is May, June, winter version, which is October, November, as well as the Feb, March version, so that we have the full breadth of papers to be able to provide us with rich data on what concepts are tested. So if I look at the forces in motion topic, there are 4 commonly tested concepts. The first is the distinction between mass and weight, right? So this topic is a favorite for paper 2. Every paper 2 that I've looked at between 2020 and 2022 had a question on this topic, so that's an easy 1 mark in that paper. So essentially here you need to be able to distinguish between mass and weight, which we'll look at, as well as be able to apply the formula to be able to calculate either weight or mass when the other quantity is known. The next commonly tested topic is around resultant forces and or momentum calculations. So resultant force essentially is, so if you had seen my previous video, chapter 2 on motion, we looked at how to calculate resultant velocity using vector addition. So resultant force questions are going to be very similar to that. The resultant momentum questions are going to be more focused on the interaction between two bodies, such as in a collision, and how their momentum tends to change. It also tends to look at the concept of momentum conservation, right? So this particular topic is tested in both papers. It's tested in 2/3 of paper 2s that I looked at, and in a third of the paper 3s that I looked at. So again, very important concepts as far as this topic is concerned. The key topic I would say is obviously the application of force, momentum, and impulse formula. So this is essentially being able to use the equations for these three different quantities to be able to obtain them from the information that's given in the question. So again, they're very common in both paper 2 and in paper 4. I'd say it's the most commonly tested topic overall. And then after that, you have to be able to describe how these different quantities tend to change in different situations. We'll be looking here at circular motion. We'll also be looking at freefall. So if you've seen the video that I made for chapter 2 on motion, I've covered how the motion of a body changes when it's in freefall, like when is it accelerating, when is it decelerating, when is it at terminal velocity. However, in this video, we'll be looking at how the forces in the body tend to change as the body is free falling. And we'll tend to do that for circular motion as well. We tend to look at the forces acting on the object. So now if we dive deeper into the concepts, I want to start off with the formulas looking at forces in motion. So force, which I'll call in terms of F, is equal to mass times acceleration, or is equal to ma. So if you look at the bottom here, we've essentially got a body of mass m. We've got a force F acting on it. This force acts over a time t, and because of this force, the object, which was initially moving at a velocity of u, moves now at a velocity of v, right? So u is the initial velocity, v is the final velocity, t is the time over which the force F acts, and m is the mass of the object. So force F is equal to mass into acceleration. So the units of force is kilograms meter per second square, so that's the SI units. Because mass is measured in kilograms, that's its SI unit. Acceleration is measured in meters per second square, that's its SI unit. But the most common unit that you tend to use for force is the Newton, right? So the Newton is the most common unit of force, and essentially 1 Newton is the force you need to be able to make an object of mass 1 kilogram accelerate at 1 meter per second square. So that is what a force of 1 Newton essentially means. The thing to understand as well is that essentially an object will only accelerate if there is a net force acting on it. Now we will look at this in the different real life examples we see, such as in circular motion or in free fall. But if there is no net force, which means the force is zero, then usually either mass has to be zero or acceleration has to be zero. Typically mass is not zero. That every object in the universe that we are looking at will have a mass, however small it is. So the mass cannot actually be zero. So that usually means that when force is zero, the acceleration of the body has to be zero, which means that unless a net force is acting on an object, the object will not accelerate, right? So for example, in this instance, if we had an equal and opposite force act on this side of the object, then essentially the object is not going to accelerate. It's going to either continue at its same velocity u, or it's going to or if it wasn't moving at any velocity before, it's going to stay stationary. Right. This is also one of Newton's laws of motion, which says that an object retains its state of motion unless acted upon by a force. Okay. So if I move into momentum, momentum is given the symbol tiny p, and that is equal to mass m times velocity, and here I've given velocity as u or v. So if I was to calculate the initial momentum of the object, so what was the momentum before the force acted on it, that would be the mass times the initial velocity, so that would be mu. If I wanted to calculate the final momentum, that would be the mass times the final velocity, which is going to be mv. Here I've just given mv to give you an example of what the calculation of the formula for momentum will be. And the units of momentum, the SI units are going to be kilogram meters per second, because the SI unit for mass is kilogram. The SI unit for velocity is meters per second. So momentum will be measured in kilogram meters per second. So essentially, momentum looks at the velocity that a body with mass has when it's moving, right? The next thing is the change in momentum, right? So if I wanted to find the change in momentum, I want to be able to subtract the initial momentum from the final momentum, right? So the final momentum, as we've seen, is the mass times the final velocity. To be more precise, it's the final mass times the final velocity. So this is assuming, the object is, say, for example, in a collision, and it shatters and its mass is reduced. It's not the same as before, which means the final mass is going to be different from the initial mass of the object. So you'd have to take into consideration the final mass. That being said, in like almost every momentum question that I've seen in your GCSE papers, you will find that the mass of the object does not change. It tends to be constant, right? So here we just assume that the mass, or especially in this particular instance here, we just assume the mass remains the same, because there's no earth-shattering collision on this object. So you just have the mass multiplied by the final velocity to give you the final momentum, and then you got the mass multiplied by the initial velocity to be able to give you the initial momentum, and then you've got mv minus mvu. Because again, I said the mass doesn't change for the object in the scenario, you can take the mass out because it's common between the two terms here. And that will give you m, which is the mass, multiplied by v minus u, which is the final velocity minus the initial velocity. Now, the change in momentum is also called the impulse. So the definition for impulse is the change in momentum of a body when a force acts on it for a period of time, right? So that's what impulse is. So if I wanted to essentially equate force to the change in momentum or the impulse, how do I do that? So this is exactly what we'll be covering in the next slide. So we'll start off with the formula for force. Again, we've got the same system as before. We got an object of mass m with an initial velocity of u, which has a force F acting on it over time t, which results in a final velocity of v. So the force of this object is going to be the product of its mass and the acceleration. Now, the acceleration, if we go back to the topic of motion, if you look at my video on the topic of motion as well, you will know it's the rate of change of velocity, or it's the change of velocity over the time during which this change happens. So in this scenario, the velocity changes from u to v, so the change in velocity is v minus u, and this happens over a time t. So the acceleration is equal to v minus u divided by t. Now, if I substitute this expanded form of acceleration into my original equation for force, I've got force is equal to mass times the change in velocity divided by time, right? So that is equal to mass multiplied by the final velocity, minus mass multiplied by the initial velocity, the whole thing divided by time. So that is the new definition I have for force when I've expanded out the formula for acceleration. Now, we know from the previous slide that the mass multiplied by the final velocity is the final momentum, the mass multiplied by the initial velocity is the initial momentum, and the difference between the two is the change in momentum or the impulse, right? So which is what I've got here in my fourth line, which is the change in momentum is equal to the final momentum minus the initial momentum, that's also equal to the impulse. So then if I plug this in to what I have here in this equation, if I plug that into the numerator, my force is equal to the change in momentum over time, or it's equal to the impulse, because impulse is the change in momentum over time. So you can also think of force as the rate of change of momentum, as this equation shows, or you can also think of force as the rate of change of impulse. Or another way of thinking about it is that the rate of change in momentum is the product of force multiplied by time, which is the same as impulse, right? Because I said the definition of impulse is the change in momentum of an object because a force acts on it over a period of time. So impulse would here be the product of force and time. So this is how you would link up momentum, or rather changing momentum, impulse, and force. And it's very important that you are able to do this, because a lot of sort of 3-mark questions in your theory paper especially expect you to be able to interchangeably work between these different quantities. So the information that you'll be given in the question would have some of these quantities, but will be missing the others. So you have to be able to link them up, as we've done here, to be able to calculate the final quantity that they're interested in. So if I now move on to the concept of the conservation of momentum, right? So conservation of momentum states that the total momentum of a system is conserved at different points in time, right? So if I took a system which has two objects, let's call them object A and B. So I say that object A has a mass ma and an initial velocity ua, and object B has a mass mb and an initial velocity ub. You need to keep in mind here that essentially what I mean by ma and ua is, so mass is denoted in terms of m, velocity is denoted in terms of u, and the mass pertaining to A is denoted in terms of m subscript A. The initial velocity of A is u subscript A, and the same has been done for B, so I've called it mb and ub, right? So I've got an initial state, which is shown by t initial, and then these objects collide, and then I've got a final state, which is shown by t final. And here, the masses still stay the same. So object A has a mass of ma, object B has a mass of mb, but now they've got final velocities, which is va. So v is the symbol for the final velocity, and if it pertains to A, it's va. If it pertains to B, it's vb, right? So what we're saying is that the total momentum of the system, right, has to be the same throughout. That is the conservation momentum, which means that the initial momentum of the system has to be equal to the final momentum of the system. And what do I mean by that? So the initial momentum of a system can be calculated as the momentum of its components, right? And what I mean by the components is the different objects within the system, right? So initially, you can see that you got two objects here. One has a mass of ma and a speed of ua initially. The other has a mass of mb and a speed of ub. So the initial momentum of object A is ma multiplied by ua. The initial momentum of object B is mb multiplied by ub, and the sum of those two gives you the initial momentum of the system. Then you've got the final momentum of the system, and the final momentum of the system is going to be the final momentum of A, which is ma multiplied by Va, and you add that to the final momentum of B, which is mb multiplied by Vb, right? And the total of this has to be equal. Now, the key thing to keep in mind is that we're saying that the momentum of the system, right, of both of these objects which form the system is conserved. It's not that the momentum of A or the momentum of B in itself is conserved. And I think this is a very good example to see that, because if you look at B, for example, initially B has no velocity. Yeah, so if I was to simplify this equation, I would just omit this term. I would just say the initial momentum of the system is MAUA. But I've just kept it for example, so UB could be any velocity. We've just assumed it's zero here. So what I'm saying is B initially has no momentum before the collision with A, but then after the collision with A, B has a momentum. So if you just isolated B in the system, you can see that the momentum is not conserved because B initially starts off with zero momentum, suddenly it's got momentum. But that is only looking at half the picture because, or rather, well, half the picture here because there's two objects, but that's rather not looking at the full picture. And the reason for that is because the momentum that B has gained is equal to the momentum that A has lost, because A was initially traveling at a velocity UA, which is greater than the velocity VA. And you can see that by the size of the arrows. You can see that, VA is a much smaller arrow than UA, right? But in the final system, both A and B have a velocity. So the gain in velocity by B must equal the loss in velocity by A, so that the total momentum of the system at the initial stage and at the final stage is equal. So that is essentially what the conservation of momentum says. It's not saying that the momentum of one of the two objects or one of the many objects in the system is conserved, but rather it's saying that the total momentum of the system is conserved. So if one object within the system gains momentum from the initial state to the final state, then another object has to lose it. And that is what the principle of conservation of momentum is. So the next commonly tested topic, especially in paper 2, is your ability to first distinguish between mass and weight, and then also to be able to calculate mass or weight given the other quantity. And I think the very important thing to keep in mind here is that, firstly, mass is the amount of matter, the amount of substance that an object has, right? So it's what you see when you weigh something, or when you stand on a weighing scale, what you see as the weight, what we call the weight. And I think the reason why this concept tends to confuse a lot of people is in our daily vocabulary, when someone asks you for your weight, what they're actually referring to is your mass, right? So when you say, for example, you weigh 60 kilos, what you actually mean is that your mass is 60 kilos, so the amount of matter you have is 60 kilos. It's not the fact that you actually weigh 60 kilos, right? But that is, again, obviously, if your doctor asked you what you weighed and then you said you weighed a certain number of newtons, because weight is a force, then they're probably going to look at you funny, right? So the key thing to remember is that mass is the amount of substance something has. It's measured in kilograms. Weight, on the other hand, is the force of gravity acting on the mass of the object, right? So if you weighed 60 kilos and the force of gravity on the surface of the Earth is 10 Newton, so it's the gravitational acceleration rather is 9.81 meters per second square, then essentially what we're saying is that because of the force of gravity, your mass of 60 kilos will accelerate towards the Earth at 10 meters per second square. Or rather, the force acting on you, because we know that force is mass multiplied by acceleration, and in the case of force due to gravity, that acceleration is going to be the gravitational acceleration. If you had a mass of 60 kgs, then your mass multiplied by the gravitational acceleration, which we've assumed is 10 meters per second square, gives you a weight of 600 kilogram meters per second square, or we know that force is measured in newtons, so it gives you a weight of 600 newtons. So the key thing to keep in mind here is that mass is the amount of matter you have. That will stay the same, whether you're on the moon, whether you're on the International Space Station, whether you're on the surface of the Earth, whether you're falling towards Jupiter. Hopefully you're never in that situation. It's going to be the same, right? And it's measured in kilograms. What tends to change is the weight, because the weight depends on the force of gravity, and the force of gravity depends on a number of factors. It depends on the mass of the object that's attracting you. So, for example, the reason the force of gravity is different on the moon versus the Earth is because the Earth is much bigger than the moon and is much more heavier than the moon. So the Earth has a stronger gravitational field. The force of gravity also depends on how far away you are from an object. So, for example, right here on Earth, the force of gravity due to the Earth is greater than the force of gravity due to Jupiter, even though Jupiter is several thousand times bigger than the Earth. But so the force of gravity depends also on how far away you are from the gravitational influence of a body, right? And the weight essentially is the force of gravity acting on your mass. That is what the weight is. And weight, because weight is a force, weight is measured in newtons or kilogram meters per second squared, as we've seen. So here's essentially what I've said. So I've said g is the gravitational acceleration. Exact value is 9.81 meters per second square near the surface of the Earth. But this can vary by the celestial object, as we've seen. This could, we saw from the examples of the Moon and the Jupiter. It can vary based on the heaviness of that object, as well as the distance that the body is from that celestial object. The other thing that I would keep in mind is in your papers on the very front page, it will either ask you to estimate g to be 10 meters per second square, or it will ask you to calculate with 9.81. I think from 2023, the papers have asked you to calculate in terms of 9.81, but in the past before that, you could assume g to be 10. So it's very important that you keep that in mind. If the paper asks you to use 9.81, please use 9.81. But if they ask you to use 10, then it does simplify your calculations, but you can use 10. And yeah, again, the point to take away from this is that if you were at any point in the universe, it doesn't matter where you are, how far away from an object you are, your mass will be the same, right? Your mass is inherent to you. It will, be the same. It's always measured in kilograms. Whereas the weight will change depending on which object you are near, how far away from the object you are, what is the gravitational acceleration near the surface of the object, and you have to remember the weight is a force, and therefore it's measured in newtons or in kilogram meters per second square. So that is the distinction between mass and weight. So now we're going to look at the concept of resultant force. This is not that dissimilar to what we've seen in chapter 2, where we explored adding velocities together. Essentially, it's a matter of vector addition, but here we're just doing it with forces, really. So that's the only difference. So I've got an object here with a mass m, and it's got 4 forces acting on it. There are 2 forces acting in the vertical direction, F3 and F4, and there's 2 forces acting in the horizontal direction, F1 and F2. These forces are all perpendicular to each other, right? So you can see that F1 is perpendicular to F4 and F3, F3 is perpendicular to F2 and F1, so each of the adjacent forces are perpendicular to each other. And sticking to the convention that we had earlier, that we explored in chapter 2 as well, we say that the forces that are acting upwards in the vertical direction and they're acting to the right in the horizontal direction are positive, whereas the forces that are acting downwards in the vertical direction and that are acting to the left in the horizontal direction are negative. And essentially, this is just a way of assigning a direction to a force. So we could see that F4 is a force that has a value or a magnitude of 15 newtons but acts downwards, essentially giving it a value of minus 15 newtons as a vector. Right, so the first thing that I've started off with is I am trying to calculate the vertical component of the force. I'm trying to get the net vertical force. Yep. I've called it Fy, and the reason I've called it Fy is because the y-axis is the vertical axis. Here we've got essentially two forces that are in the vertical axis. So we want to see the net force in the vertical axis, which is Fy. So we are adding F3 and F4. So we're not including F1 and F2 because there is no component of F2 or F1 that is acting vertically. So this is a fully horizontal force with no vertical component. The same is true with F2. So if we took F3 and F4, we want to add them together to be able to get the vertical component of the force Fy. So F3 acts upwards. It's got a value of 10 newtons, so it's going to be plus 10. F4 acts downwards and has a value of 15 newtons, so it's going to be minus 15. So that gives you a net value of minus 5 newtons or 5 newtons downwards. And this makes sense, right? Because if you looked only at the vertical forces, F4 is the greater force than F3, and it's greater than F3 by 5 newtons, and it's acting downwards. So that makes sense, and you want to assign it a value of minus 5 newtons. Now, if you look at the horizontal component of the forces, we've called it Fx because x is the horizontal axis. And then you've got two forces acting there, F2 and F1. I've said, again, like as we explored earlier, neither F3 nor F4 have a horizontal component. So, for example, F4 is pointing like that at an angle, then it would have had both a vertical and a horizontal component, but it doesn't have a horizontal component, and the same is true for F3. Therefore, we'll only be considering F1 and F2. So f of x is equal to, well, I've said F2 plus F1. F2 is 50 newtons and acts to the right. F1 is 10 newtons and acts to the left, but because it acts to the left, it's minus 10 newtons. And Fx, the net horizontal force, is 5 newtons acting towards the right. And this makes sense, right? So we've got a net 5 newtons acting towards the right and a net 5 newtons acting downwards. So here we want to try and find the resultant force, which is the net total force. That is, it's irrespective of whether it's horizontal or vertical. It's like the net force, what direction does it act in? So the first step to be able to do this is to create this vector triangle. So we start off with one vector. We know the vectors have a tail and a head. So we've got that here, Fy with its tail and head. And we know that we have the head to tail logic of adding vectors together. So when I want to add Fx, I want to assign the tail of Fx to where the head of Fy is. And then the blue vector that we see is the resultant vector. Its tail starts where the tail of the first vector, in this case Fy, is present, and its head ends where the head of the second vector is present, which is Fx. So there's two ways of being able to obtain the value of F, the resultant force. So one way is by using the scale method, where essentially you draw out the vector triangle at a scale that you've assigned. So for example, if I took a scale of 1 centimeter equals 1 Newton, then I would have this arrow here to be 5 centimeters long, that's pointing downwards. I would have this arrow here to be 5 centimeters long, pointing towards the right. And then all I would have to do is I would have to join them by drawing this resultant force here. And to find its value, I just need to measure its length. And once I measured its length, I will get a value in centimeters. And then I would just have to apply that value to the scale that we assigned to be able to get the value in newtons. So in this case, we said 1 centimeter is 1 Newton. So if I measured the length of this out, which we've calculated to be 7.1 newtons, you would get a length of 7.1 centimeters, and then you'd apply the scale, and you'd be able to get a value of 7.1 newtons. You would also typically be expected in these questions to calculate the angle between the vertical component and the angle between the horizontal component. Again, the easiest way of doing this is to just use your protractor to be able to calculate the angle. So this is fairly straightforward math, but you just need to place the center of the protractor there to be able to calculate this angle, and the center of the protractor around here to be able to calculate this angle. So that's how you do it using the scale method. The scale method is a straightforward method if you got non-right triangles. So for example, if these vectors were oriented not perpendicular to each other, but at an angle to each other, that is not 90 degrees, then it's a good place to use the scale method. The scale method is also useful if you're not comfortable using Pythagoras and trigonometry. All you need to do is make sure that you stick to, you establish a scale conversion, and then you stick to that scale conversion, and you should get the right values for the resultant force as well as the right angles. The method that I've used here, because we are dealing with two component vectors that are perpendicular to each other, hence forming a right triangle, is like essentially the Pythagoras method, where we know that the square of the resultant vector or the resultant force is going to be equal to the sum of the squares of the component vectors or the component forces. So again, substituting the values of phi for fx and phi for fy, I basically get a value of 7.1 newtons for the resultant force. So that is my resultant value. The next concepts we're going to be looking at circular motion. We're going to be looking at free fall, although we did visit free fall in our notes from chapter 2. So circular motion, again, you get questions from this topic where you are expected to describe the direction of force and the direction of motion of the object. But I think before I get into that, I just want to explain or explore rather how an object moves in a circular path. So we know that velocity of an object is essentially its magnitude and its direction. And we know that a change in the velocity can be caused by a change in either the magnitude or the change in direction or a change in both, right? And we know that when velocity changes, we have an object that accelerates. And if we went earlier into the chapter, we also explored the concept of force and acceleration. So we said when there's a net force, an object is going to accelerate. When there is no net force, then the object is not going to accelerate, right? So these concepts are fairly straightforward, So if velocity changes, there is an acceleration, and if there's an acceleration, there's usually a net force acting on an object. So if you've got an object moving in a circle, even if it's moving at a constant speed, so say its speed or the magnitude of its velocity is the same everywhere across a circle, at each point in the circle, the direction of motion of the object changes. So if you want to know the direction of motion of an object at any point in the circle, you have to take what's called the tangent to that point. So if we assume that the object was at this particular point here, that's the edge of the circle, if you drew a tangential line there, this gives you the direction of motion of the object at that particular point in the circle. Say the object was down here at the bottom and it's moving in this anti-clockwise direction, then you're going to have a tangent that is towards the right. If it was around here and it's moving again in the anti-clockwise direction, it's going to be pointing upwards. So if whatever is keeping the object moving the circular motion is relieved, then the object is going to travel off shooting upwards like that. And then when it's at the top here, it's going to have a tangential direction moving towards the left. Yeah, so just at these 4 points, but at every point really, the direction of motion of the object changes. So if the direction of motion changes, the velocity is changing at every point in a circle. And the velocity changing at every point in the circle, the object is accelerating throughout its circular motion. And if it's accelerating throughout its circular motion, that essentially means that there is a force, a net force acting on the body. So what is this net force? So this net force is essentially called the centripetal force, right? This force always acts towards the center of the body, and this force is responsible for keeping the body moving along a circular path, right? And without this force, if this force gets snapped for some reason or disappears for some reason, then the body is going to start traveling in the tangential direction at the point where the force, the centripetal force disappears, right? So key thing to keep in mind is centripetal force is what enables an object to move around in a circle. Even if it's moving at a constant speed, it's still accelerating because its direction is changing at every instance. And if this centripetal force disappears, the object will travel off in the tangential direction at the point when the force is released. So the way I'd like to think about it is if you had a string and then you tied it to a ball or a marble or whatever, and you spun it, essentially if the string snaps, then the marble or the ball is gonna shoot away at the point where the string snaps. So it's no longer moving circularly, but it starts taking a linear path of motion. The same would happen if, for example, the Earth disappeared tomorrow. Then the Moon and the various various artificial satellites that are around the Earth would start sort of moving off in a tangential direction at the point that the Earth's gravitational force disappears, right? And this is true for all of the celestial bodies as well, like the planets to the sun to the greater forces B in the Milky Way galaxy. So this is essentially what is happening. So usually questions from this topic will ask you to mark the direction of the centripetal force. That's always towards the center. So we can see that for the object at this position, it's pointing towards the right, towards the center of the circle. If it's at the bottom, it'll be pointing to the top. If it's on the right, it'll be pointing towards the left to the center. And if it's at the top, it'll be pointing right downwards towards the center of the circle. And you will be asked to mark the direction of motion, which is, well, perpendicular to the centripetal force and is essentially tangential to that point on the circular part. The next thing that we're going to look at, and you have seen this graph before, this is from the CAIE IGCSE Physics textbook, and I used this previously to explain the concept of motion during an object that is falling first freely and then after that using a parachute. But here we're going to explore the same speed time graph, but we're going to explore it by looking at the different forces acting on the object. So if we start off with this point here, when an object is released into the atmosphere and has nothing stopping it from sort of falling towards the planet, it's essentially the force of gravity acting on its mass, so that's the weight, and the object is accelerating because a net force is acting on it. But as the object falls through the atmosphere, there is going to be the force of air resistance that's resisting its motion, and this force of air resistance builds up and up and up till essentially the force of gravity is balanced by the force of air resistance. And when this happens, there is no net force acting on the object, which means it's traveling at a constant velocity, which we've already seen is termed the terminal velocity. So we start off with an initial phase of a constant acceleration, and then after that, the rate of acceleration or rather not decelerates, but the rate of acceleration slows down because air resistance is getting stronger and stronger till eventually air resistance balances the force of gravity. The important thing to keep in mind is that the force of gravity is not getting weaker. The force of gravity remains the same near the surface of the Earth because the gravitational acceleration is the same near the surface of the Earth, and essentially the mass of the object is not going to change during the period of fall. But it's important to keep in mind that the air resistance only slowly builds up. So initially there is a lot of acceleration, and the rate of acceleration slows till you eventually get to terminal velocity. And once the parachute opens, obviously parachutes provide a massive surface area, so there's a lot of drag, especially at the speed at which the object is falling, there's a lot of drag. This drag is captured by the parachute, and that results in a massive deceleration. So the force of gravity is still the same, but now the drag is just so high that the object tends to decelerate. But then the rate of deceleration again slows because, as the object velocity is reducing, the drag on the object reduces. And again, if I use drag, I basically mean air resistance, so I'll use them interchangeably. So when the drag on the object reduces, what happens is eventually you reach another area where the downward force of gravity is balanced by the upward force of air resistance, and that results in a zero net force or zero acceleration, which results again in a constant motion or a new terminal velocity. So that is essentially how the forces are in interplay in the speed time graph when an object is falling. Again, the key bits are you should be able to describe how the forces change in these different areas. And the key thing to remember is the force of gravity stays the same. It's only the air resistance that changes depending on whether the object has just started falling or whether there is a parachute open. And I think the air resistance is proportional to the velocity of the object. So the higher the velocity of the object, the higher the air resistance tends to be. So I hope you found this video helpful. I hope you're more confident now in the concepts, or the key concepts rather, within the forces in motion chapter. If you found this video helpful, then give it a like and please subscribe and share the channel with others who you think will also benefit from the content that I make. Thank you very much.